thank you all for coming, and okay, let's get started. So let's keep talking about observational study. So today we are going to focus on the robust estimation of a propensity score. So as we know, so this is the fourth topic of this serial topic on observational study. So in the first one, so I gave a brief overview of the observational study. So in terms of the conceptual definition, the types of study design, and the advantage and the disadvantage of each type of study design. And I also introduced a very interesting instrument variable-based approach, so to avoid very strong, so no hidden bias assumption in observational study. So after that, so in the second and third topics, so Dr. Zhu Zhang introduced the propensity score-based approach for the bias adjustment in observational study. He focused on the propensity score matching and the propensity score weighting method. So today, so it's the fourth talk, also is the last one. We're gonna talk about how to improve the robustness in estimation of a propensity score. So it's a very interesting and important point. This is the outline of my talk. So it consists of 3 different sections. So in the first one, so I will give you a brief review of the propensity score in observational study. So it's not just the simple repeat. So I would like to share some fundamental understanding and the properties of this propensity score and how to estimate this propensity score based on the logistic regression. The second part is the robust estimation of propensity score. So this is our main part in this talk. So it includes some different methods in contrast with the very classic logistic regression. So it includes the Bayesian method, a class of the machine learning method, and a very interesting covariance balancing method. And finally, I will end my talk with summary and conclusion. Let's go to the part 1. Well, so as we know, so we're interested in investigate the relationship between some treatment exposure and outcome of interest. And however, in observational study, we know we cannot get that effect or estimation directly since there's some existing confounding in that kind of studies. So the central issue in observational study is to ensure the comparable group are compared and some competing treatment. So it means we would like to create or adjust the study through some observed covariance to make it look like a randomized control trial. So before we start to introduce some specific method, so I would like to introduce a notation in this talk. So let's assume this Y is the outcomes of interest, and G is the indicator variable of treatment assignment. So in this talk, we only talk about the binary treatment studies, which means exposure and unexposure groups. So we assume they equal 0 or 1 to indicate a different treatment group. So we're interested about to estimate the average treatment effect, also being called a causal effect, which can be defined and some counterfactual outcome framework like this. So we can define this average treatment effect is equal to the difference of the expectation of this outcome of interest given the treatment assignment. So we know for the subjects, it cannot have these 2 values being observed at the same time. Since one subject cannot be assigned to the 2 groups directly. So usually this effect, this delta cannot be estimated directly. So, however, in randomized control trial, we know so the randomization can reduce all the selection bias. So the randomization can make this estimation become real. So we can use the sample average to estimate this effect. So if in observational study, we know there is some confoundings existing, so we use the X to denote some Q-dimensional observed confounding. So I have to emphasize here is that all this confounding needed to be identified before the treatment assignment. If some variable could affect the outcome can be identified after the treatment assignment, it's a confounding. It's we call it it's a mediator. So I still use this plot to demonstrate the relationship between the treatment assignment outcome and some confounding covariates. So we can see this is our main effect we would like to detect from the treatment assignment to the outcomes of interest. This confounding, we assume this confounding affects this treatment assignment and its outcome at the same time. So if some variables being detected only affect outcome or only affect the treatment assignment, it doesn't matter. It doesn't matter. So if some confounders be observed, so we can assume when this we call the ignorability assumption holds. This assumption is given observed baseline covariates, the treatment assignment and the outcomes are independent of each other, which means given this observed X, this treatment assignment does not directly affect this Y, the rho X. So this is also being called the no hidden bias assumptions. So under this assumption, if this assumption is true, so which means that all the potential confounder has been observed, or also has been measured. So we can define this treatment, average treatment effect through this formula, given observed covariance X. So this assumption is a fundamental of the is a fundamental of the covariance adjustment, or called the bias adjustment in observational study.
And could you repeat? I'm not sure I understand. What's the ignorability assumption? Is Z equals Z given Y?
Well, Z is the indicator variable of treatment assumption, right?
Okay.
So the Y is the outcome. So that means no matter you being assigned to the treatment, a patient being assigned to the treatment or control groups, doesn't matter. It will not affect the outcome. The patient will be the outcome that will be observed in treatment and control group.
Okay.
So that means treatment does not affect the outcome. Treatment assignment does not affect the outcome. I should say that. As we know, we would like to get the unbiased estimate even in observational study. So the central issue is to do some confounding adjustment. So the common method used for confounding adjustments are to create the comparable groups through observed and measured X and ignorability assumption, just like what I said in the other slide. So the classical method we use, people like to use one is called the covariance adjustment. So in covariance adjustment, we would like to model all of these observed covariates in this effect model to use this as a covariance. So this method guarantees we can get a consistent estimate of this effect alpha. And another very commonly used method is called covariance matching. The covariance matching is very similar to the previous propensity score-based matching, since that's maybe a more advanced version, but this is a more classical version. So we would like to generate to match the groups just based on observed covariance directly, not based on the propensity score. So we know the covariance adjustment is an unbiased method with very easy implementation and interpretation. But however, it suffers some the linearity assumptions and high-dimensional estimation problem when the Q is large. We know the Q is a dimension of the covariance X, the confounding X. So this is the covariance adjustment. If this is true, we need to assume this X has some linear relationship with this outcome Y. However, this is very strong assumptions, especially when the number of the dimension is large. So we all know. So each variable being added to a model is not just add some information, also add some noise. So when the dimension number of this X is large, they're going to bring a lot of noise. So in this model, it could affect the estimation of the treatment effect alpha. So covariance matching is just the approximate estimation. So we know we cannot exactly find the two exactly same covariance, especially for some continuous covariance. So it becomes not applicable if the number of this X, the dimension number of this X is large. So we can match. So we can match the gender, age, or insurance type. So from the two different groups. However, if we have a 10 or 20 even more different covariance, especially for some continuous covariance, it's difficult or it's not possible to make the covariance matching method. So this is a very strong limitation of this classical adjustment method. So because of this, so in 1983, so Paul Rosenbaum and Don Rubin introduced the concept of the propensity score. So the idea or the definition of the propensity score is the probability of assignment to a particular treatment given the observed pre-treatment covariance. So this is the formula actually by the definition. So for example, if we would like to model the patient be assigned to the treatment Z equal 1 given observed X, is this, so this probability we can call this is the propensity score. So we know this propensity score is greater than 0 and less than 1. Under this definition and the ignorability assumption, so it's ready to show. So the average treatment effect between these two groups given all the observed covariance X is equal to the same formula, just the given propensity score. So this is a very big breakthrough. The most important issue is so this X could be a high dimensional data, and this propensity score is just a one-dimensional scale. So the dimension reduction to make this model, we can simplify this original model to this one, just given on one-dimensional data. So this gives us a lot of benefit. The most important benefit is in some way we know the big data or the large-scale data become more and more popular. So it's become very easy people to get the large-scale data. And however, the classical inference is hard to fit the model to the large-scale data. And so we can, if this dimension reduction is true, so we can easily to get estimation just based on one scale data. And another issue is another benefit is we don't have to specify the linear relationship between this propensity score and the outcomes, like we mentioned in previous slide. So I would like to mention two important interpretations about propensity score. So usually we know the definition, and we sometimes we even know how to use this propensity score. But before we use that, we need to understand what does the propensity score really mean. So in a bias adjustment method. So first we know, given on the definition, so we know the propensity score is the probability of treatment assignment. So it can be interpreted as a probability of treatment assignment, like a sampling weight. So that means if you be assigned to or be selected to some treatment groups, so this will become the weight. Another interpretation about the propensity score is it's a score or weight on covariance balancing. So based on this this scale, or based on this value, we would like to create a balanced covariance. Okay, I just introduced the two interpretations, but later we're going to see how we understand this interpretation, or how we use this interpretation on the different probability score-based method for the bias adjustment in observational study. So here, I'll give you an example of the probability score distribution. So we still use the two treatment group as an example. So this dash curve is a distribution of the estimated probability score for some particular sample data. And this solid curve is a distribution of probability score for some treated sample data. So we can see, so this is not always true, but this is just an example. So we know if these two curves exactly overlap each other, so this is a randomized trial. So if these two curves just isolated, there's no any overlap. So just like Zuki said, we don't have to do any. We don't have to keep doing that. Doing anything on this study since this two is not comparable. So this is a very common issue. So we may meet in some observational study, and so in this part, so we can see this has been never treated since there's no any overlap between this probability score with the probability score from the treatment group. So in this part is been the always treated group. So usually we don't care about these two groups. We care about the subjects between these two. And we would like to create or generate a compare group just based on this group. So probability score matching. I don't want to. We know we have the whole seminar to introduce this probability score matching method, but here I will not repeat that, but I will give you share some fundamental understanding about this method. So the key point of the probability score matching is a balance between the comparable groups on all covariates. So the idea is we would like to generate or create a two group with equal or balanced the covariates. So which use the probability score interpretation as the covariance balancing score. So for probability score matching, we don't care. Actually, we don't care about it's the probability of treatment assignment or not. What we care about is we would like to create a score. So this score can optimize the covariance balance. So look, based on this formula, so we would like to generate some balanced probability score, which could make sure we have an optimal covariance balance. So this method is easy to implement and interpret. And also, like what I said, it requires optimal covariance balance. So also, for all matching method, it can only give you an approximation of average treatment effect because we know the probability score is a continuous value. So usually in practice, we cannot find exactly same two probability score from two explorer groups. Also, it needs a relatively large sample size, especially for the control group. So we still use this plot as an example. So when we do the probability score matching, we only care about the patient in this area. So we can match the patient who exactly have the same or the very close probability score. So only focus the patient in this area. So all the patients in this area we will not use. So we may need a relatively large sample size. Otherwise, we may not have enough power just based on this part of subjects. So on the contrary, so probability score weighting is another technique. So probability score weighting method is to apply probability score as a sampling weight, just like what I said before, to create a balanced comparable group, which uses probability score interpretation as a probability of assignment. So in this method, we may not care about this score exactly optimize the covariance balance or not. We would like to find so this propensity score give us the sampling weight. This sampling weight is like a treatment sampling, so you'll be sampling to the treatment of explorer group or non-explorer group. So here I give you an example. So we may estimate the treatment effect, average treatment effect, based on the propensity score weighting. Like we only weight the patient in control group to make this control group looks like the patient in explorer group. Definitely, you can also weight both, and to make the subjects in two groups look like each other. It's a different technique. So here the weight is based on the propensity score. So propensity score weighting will give us the unbiased estimation on average treatment effect. As well as so this propensity score is a correct estimation of the probability of treatment assignment. And like what I said, it requires the probabilistic model interpretation for the propensity score. And it may not need it need just a relatively large or moderate sample size. So different with the propensity score matching, only focus on the patient in this area. So propensity score matching, so interested in the patient in both this area, the overlap of these two in this interval. So it may not need that large of sample size, but it still can get the unbiased estimation of the average treatment effect. But since it's the weight, sampling weight, it may be sensitive to the model misspecification. So we can think about if this weight have the maybe teeny tiny error, it could generate a very large error in this estimation of the average treatment effect. So it could be very sensitive to the model misspecification. So of course, the propensity score matching and weighting are the most popular method for the propensity score based adjustment, but it's not all of them. So other propensity score methods have been also developed to reduce the selection bias based on the different adjustment strategies. So such as we also can use a propensity score stratification method. So that means given on the estimated propensity score, so we can stratify the group. We can stratify the patient from the explorer and unexplorer group to the different strata. So this strata just defined by the estimated propensity score. So usually we may use a different. This strata may be different, may be defined by the different quantile of this estimated propensity score. So given on the quantile of the propensity score, so we can estimate called the strata effect, and we also can combine the effect from each strata and to estimate the overall effect. So also we can use the propensity score as a covariate to do the model adjustment. We instead of just like the previous called the covariance adjustment, we use the propensity score as a covariance directly. So we can also, if this is correct model, so we can also get a consistent estimate of this alpha. However, the problem is just like what I said before. We need to assume the linear relationship between the propensity score and the outcome of interest. So usually, it may not be true in practice. So this is not our main part in this talk, but I would like just to give you some introduction about score-based method. So we know the propensity score has a very beautiful mathematical and statistical theory, and also can give us very exciting tools to help us to do the model adjustment. So, but however, the real problem is the true propensity score is unknown. We have to estimate it. So through some statistical modeling. So in practice. From the vast majority of the published literature on propensity score estimation, so we know the logistic regression is one of the most commonly used methods in practice. Well, actually, I should not say the one of the most commonly used. It is the most commonly used method in practice. So because I think because it's very familiar to almost everyone, so everybody knows what the logistic regression is. And also, we know the logistic regression has a pretty good, mathematical and statistical property. So give us a beautiful, mathematical framework. And also, it's very easy to implement and interpret. Almost all the software has a logistic regression, and we know we can interpret the model parameter as log observations. And also, it's based on the probabilistic framework. We define this propensity score as a probability based on this logistic function. So, although logistic regression is a very, very popular model, however, we cannot just use it naively and without any model validation. So as you remember, I talked with Rachel before, with one of our intern students, and she asked me about a study use the propensity score method to do the model adjustment. But however, she just told me the investigator just use all the observed or collected baseline queries as a potential confounder and put it in the logistic regression model and fit it and get the estimated value as the propensity score without do any variable selection, model validation, model diagnosis. They didn't do anything about this and just use it. So it could become very dangerous. Very dangerous. So I would like to mention something here. So if you would like to do a propensity score estimation using logistic regression. So first is the identification of potential covariates. So this may not be the only issue for the logistic regression. It's an issue for all propensity score estimation method. I would like to mention here first here. So first we know that all the potential covariates could be a potential confounder because it associated with the Y, the outcome of interest and the treatment assignment Z at the same time. So if it's only associated with Y or only associated with Z, it doesn't matter. We don't have to adjust that covariate. So another concern is we need to think about some interaction and polynomial terms. We cannot just put the observed the covariates in the model and model it directly. So another big issue is so we need to check the model assumption. For logistic regression, the assumption is called the additive logic function. So that means all these observed covariates has a logic function with the probability of treatment assignment. So the logic function looks like this. So the x-axis is the value of the observed covariates, and the vertical line is the probability of treatment assignment, or we can see the probability score. So usually this is the example. So maybe this is the observed. Each dot is the observed treatment assignment. So we would like to check the relationship between the covariates and the probability of treatment assignment looks like this. This monotone S-shaped curve. So we need to check this. And for example, we can just do some simple non-parametric smoothing line and to fit the data to check that this looks like this monotone S-shaped curve. So in practice, it may not be always true. So for example, if we assume this covariate is an age, so we know this is the probability of treatment assignment. So it does not mean with the age increasing, the people has a higher probability to assign to some specific treatment. It could be with smaller age, and maybe for the younger or senior people had more probability to be assigned to some treatment, but for the middle age, it does not. So it looks like a U shape, not an S shape anymore. So it totally depends on the data you observed or the data you collected. So we cannot just use a logistic regression naively. So another big issue is so logistic regression not guarantee the optimal covariance balance. Because we know the inference for the logistic regression is based on the maximizing the likelihood of the logistic function. So it's not guaranteed. We optimize the covariance balancing. And another issue is the limitation on the likelihood-based inference for high-dimensional data. So this is actually a very big issue, obviously the common issue. So recently, since we in a lot of study, they have many covariates, and so it's sometimes it's very hard to just use a very classical logistic regression to model it, especially when with the noise, we call the ratio noise, with the ratio of noise and the signal is very large. So the motivation for some robust estimation on propensity score. So researchers have found that the slight misspecification of the propensity score models can result in substantial biases of estimated treatment effect. So the robust methods are more attractive than classic linear regression. So if the model assumptions cannot be satisfied empirically. So it's easy to understand. We definitely would like to want some model more robust, because in practice usually we cannot exactly find some data fit some assumptions that well. So we want some method which are not sensitive to the data distribution and model structure, and also it can provide unbiased or approximately unbiased propensity score estimation. Also can improve the model uncertainty and model generalization, and can be adaptive to large-scale data. So this is an important issue. Also, it provides the correct interpretation of the covariance balancing score and provide the interpretation of the probability of treatment assignment. I want to mention here is that these two may not be satisfied at the same time. So if it can, that would be good. But we may only focus on one of them because it depends on what kind of model you use for how to use the covariance balance. If you use it as a covariance balancing score, definitely we focus on this interpretation. If we use it as a sampling weight, we prefer this interpretation. Okay, let's second part. First, I would like to talk about the Bayesian method. Bayesian method as a alternative. Bayesian analysis is a very attractive method on propensity score estimation for improving model stability using prior information and Monte Carlo sampling. So usually we specify the propensity score model like this, and this model is stable because we assume the model parameter theta is fixed. We need to estimate this model parameter. If this parameter being correctly estimated, we know what the model is. However, if we would like to make this model more flexible, so we may assume this model parameter is not fixed. So, and given some prior information, so this prior information may come from the prior study or come from the other place, and it can give some information about some variability of this parameter theta. And given on Bayesian rule, we can show that the distribution of this parameter theta is proportional to the product of the classical probability model times the prior function. And we can estimate definitely through some Monte Carlo sampling method. The good thing is the Bayesian method can borrow some information from the data and prior result. It can give you more information to make you model fix your data very better. And it becomes particularly useful when the treatment population is small relative to control group. Sometimes it's very hard to find the patient on explorer group. So this model is more useful when the sample size in explorer group is relatively small. So it has a probabilistic interpretation. So we all based on the parametric distribution function. but it's not a guarantee for optimal coercive value, just like the logistic regression. It also depends. The shortage is we need to specify the prior distribution of this. This is kind of subjective, so it may depend on some your experience, or it may depend on some good mathematical format. It should depend on the choice of the researcher. We also know the propensity score method actually is a classification method. So we need to classify all the patients to the either explorer or unexplorer groups. So it has been shown that so many classification algorithms, especially from the machine learning area, can outperform classical method on propensity score estimation. So such as the logistic regression, especially when dealing with the high dimension data. So we know the high dimension data is a big limitation for the logistic regression. So, but for the classification algorithm in machine learning, it can provide some strength in this problem. So we also prefer the non-parametric and semi-parametric model-based algorithm in machine learning propensity score estimation. So for the robustness of the propensity score estimation. So in this talk, I would like to introduce just some of them, and this kind of popular method used for propensity score estimation include the neural network, the spot vector machine, the classification and regression trees, also the generalized boosting method. So each method may belong to the different small area. So neural network belongs to the artificial intelligence. Spot vector machine is one of the linear classifier. And so classification and regression tree is one of the decision trees, and also the generalized boosted model is one of the boosting algorithms. Each method may focus on the has their own advantage and disadvantage. So we would like to know them because we would like to in practice can pick the good or the appropriate method to estimate the propensity score. So let's look at the neural network first. So inspired by the structure of the nervous system, so neural network, also being called as artificial neural networks, are used to approximate the functions that depends on a large number of inputs, and also these functions are generally unknown. This is not easy to understand this, but so the neural networks consist of the multiple layers with nodes connected every node in upper layers by the direct and weighted edge. So, okay, we need to look at this before we understand how this neural network works. So this is the structure of neural networks. So it consists of usually 3 layers. So the input layer, the hidden layer, and the output layer. So the input layer definitely contains all the covariates we would like to we observed or we know. And this is the output layer, definitely generate the output. That means the patient, one patient be classified to the either explorer or non-explorer groups. So all this, the blue dot are the hidden layer. Hidden layer actually cannot be directly observed, so we need to estimate it. And each dot in the hidden layer connected all this the dots are the input from the input layer. We can think of this is something like a factor analysis. If in the psychosocial studies, this is a very typical idea. Like we generate some latent group or the latent variables. These latent variables may contain different information from the input layers through the weighted called weighted edge. So each weight. So each edge means some contribution from the input to the hidden layer. So traditionally, we don't have a hidden layer. We just extract the information from the input layer to the output directly. We model the relationship between these two. However, the neural network is we generated all the hidden layers. Each hidden layers may contain different type of the combination of the input So it's extract the information by the different strategy.
And let me ask about go back to the neural.
Okay.
So the output a propensity score or just a group?
Either way is okay. It can generate the probability of the treatment assignment, or just generate the yes or no, the binary outcome. Depends on how you specify your outcomes.
Oh, okay. So you actually could get a score.
Yeah, I could. Okay. So the neural network are trained to minimize the predictive error, through reweighting the internal edges appropriately. So we know we have some we call the training data. That means we already know the input and output. We would like to train this neural network to estimate the best weight for each edge to minimize the predictive error. So so neural network has some good properties. So first is for high dimensional data. It's especially good for the high dimensional data with a slightly effect on prediction outcomes. So we know we may have the large scale the input data, but each one maybe have just a tiny contribution for the propensity score and outcomes. So usually traditional parametric based model is very very hard to do the estimation based on that kind of data. But the neural network is more appropriate for that kind of data. Second one is sufficient complexity to approximate any small polynomial function. So we can see for each hidden node in the hidden layer, they connected all the inputs, all the nodes from the input layer. So it can generate enough approximation to the smooth polynomial functions. But the limitation is no probabilistic framework and no causal interpretation. So actually, we don't exactly know what each study means, and we cannot give a very good interpretation of the value of each study means. But we only use it as a some information combination, and to convey some information from the input to the output. And also is no hard and fast rule for the selecting the number of hidden nodes to avoid local minimum and overfitting. So the big issue is we need, it depends on some experience or expertise to select or define these hidden layers. And so sometimes the learning curve is a little bit higher. It's not easy to directly use it, but it's still a good choice for some advanced studies. So another very popular method is called support vector machine. So support vector machine is a linear classifier to find the best dividing a hyperplane based on the transformation of feature space by maximizing the classification margin. So, okay, it's also hard to understand this sentence, but I will use for example to tell you what this support vector machine means. So first, so what is the linear classifier? I use this two-dimensional input as an example. So if we have a two-dimensional input and dimension 1, dimension 2, and each dot means the different color means the different treatment assignment. So for example, on the right end, we need to classify the red dots and the blue dots. And if we can find for the two-dimensional space, if we can find a straight line to separate this two class or split this or classify this two class, I think that's great. So if it can be, can be classified by a straight line, so we call this is a linear separable. If it cannot, so it's not linear separable. This is for two-dimensional. If it's for three-dimensional case, we have three-dimensional input. So if we can find a plane, can classify these two different color dots. So we also call this a linear separable. So which means so on and so forth for even higher dimensional data. If we can, for example, for the p-dimensional data, if we can find a p-1 dimensional hyperplane to correctly classify the two different kind of color dots, so we call this called a linear separatable. So, however, the idea of the support vector machine is to maximize the margin of a linear classifier. So that means we need to find the classifier to generate our largest space between these two classes. So this is the basic idea. So, however, in real case, not all the data can be linearly separated. So especially for the case looks like this, we cannot find a straight line to classify these two dots. So maybe we need some curve. But it's hard to estimate this curve. So the idea is people would like to do some transformation to transform this input space to the higher feature space through some kernel function. You can think about this. If we have a two-dimensional data, it can be transferred to a high-dimensional data to make it linearly separatable. So this is what we want. And so the idea is that after this transformation, we would like to find a hyperplane which could generate the maximum classification margin. This is the basic idea. So some advantage and disadvantage of support vector machine. The first is the robust estimation and semi-parametric framework, like what I said. We only need for the linear non-separable, we only need to specify the parametric based transformation function. But this maximizes the classifier margin is not a parametric work, so it's called semi-parametric framework. And it's easy to handle high-dimensional input data, but it's no probabilistic interpretation. Since we did not specify this based on any probability framework, and it needed to determine the addition of the interaction and the polynomial terms. And also needed to specify the kernel functions for the hyperspace transformation. So this may not be a trivia, since it also needs some expertise and to specify this kernel function if this data cannot be linearly separable. So the classification and the regression tree. So we call the CART. The CART is a decision tree algorithm which specifies a tree of cut points that minimize the predictive error and the diversity of final nodes to using a flowchart like a decision graph or model. I also use an example for the example here. So I also use the two-dimensional data as an example. And we would like to classify the blue dot and the red dot. We assume, so maybe blue means segment group, and the red means control group. So we would like to classify this too. So the classification and the regression tree means we would like to generate a flowchart type of model or graph, and to get to minimize the predictive error through all these models. So it looks like first we would like to partition the X2 at this point to make this the input space in a two part, and we also split the input X1 based on this rule, and to find in each plot the probability or the probability score can be estimated by the average of the probability of the treatment summit. So, for example, in this plot, so we can see most of this dot is blue. So the treatment summit is about the 0.87. So this is the estimated probability score. So definitely, you can do any partition you want to make this estimation become better and better. However, this could suffer some overfitting problem to make this harder to generate to others in the data set. So the idea is we through this partition, and we would like to find a best rule to classify these two different color dots. The idea is very easy to understand and implement, and so it's a non-parametric framework. We don't need to specify any parametric form on this algorithm. And but we still have a conditional probability interpretation. So based on each partition, so we can specify a conditional probability. And based on a further, partition, you can specify a further conditional probability. So it has a probability interpretation. And the performance dealing with the construction method, and so the limitation is the performance of this modeling depends on the construction method and the amount of pruning. So like what I said, we can do any participation we want to get a better performance. However, just like this, we may partition too much for this x1 level. So we may partition too much. So it could reduce the model generalizability. So sometimes we need to do some pruning and to make sure we can get the best model performance. So when many queries are uncertainty, the calculation can get very complex. So if the data in some dimensional distribution is not that stable, it could change, very, dramatically. So we need to add more partitions. Otherwise, we cannot get better performance. So it could cause some issue. My talk. And the boosting algorithm. So the boosting algorithm is called a meta-classification method. So the idea is we assume some single classifier may not be performed very well. So we would like to combine some ideas from multiple classifiers. So it is very useful, particularly when training a single classifier for high performance is difficult or require extensive expertise in training algorithms, or it can combine the result of many weak classifiers. So their performance only slightly better than chance. So maybe only contribute very tiny information for the classification. So we can form a single stronger classifier. So boosting algorithm has some positive and negative properties. So first is less expertise. Like I said, we would like to combine some simple single classifier to form a stronger classifier. So for each single classifier, it's simple, so it's less expertise, not flexible, and also it provides the probabilistic framework interpretation, and less susceptible to overfitting than a single classification algorithm. Since we each add iteratively, we each just add one more, just add one single classifier to improve some of the model performance, and we just gradually to add more until we get the best model. And the disadvantages is no interpretation of a model coefficient. So it's statistically, yeah, we also say this is some bad limitation. I will in the interest of time, I will ignore this generalized boosting models. So this is one of the boosting algorithm. So people usually use in statistical estimation in practice. So this is an example how we use the boosting algorithm to classify iteratively classify the data. And covariance balancing method. So we also know logistic regression is still attractive for its multiple strengths in statistical estimation. So it's possible to get a solution to overcome its existing limitations on logistic regression. So that means we would like to use the logistic regression framework, but we also would like to have the optimal covariance balancing interpretation. So this idea was introduced by Dr. Imai, a professor from Princeton University. Actually, I met with him once, and we were in a same session of on conference, and his presentation just after me. So he just introduced this method. So I was very lucky, to have a chance to learn this method through that conference. And I will ignore all the formulas and So I use this method in one of my study. Actually, I collaborate with Debbie Aronsoff on her mother-baby studies to investigate the relationship of the infant feeding to the risk of child obesity at age 4 from a diverse community-based cohort study. We adjust the selection bias on exclusive and non-exclusive breastfeeding by modeling the identified 11 unbalanced baseline covariates, which include race, insurance, the marital stage, education, so on and so forth. So this is one of the results. So we compare the main effect on the BMI Z-score and the BMI 85 plus. That means we dichotomize the BMI to the normal and to the obesity group. And so we compare the unadjusted model estimation, adjustment based on the logistic regression, and adjustment based on the coherence and balancing method. So we can see the logistic regression. So is sensitive to data distribution. So it's over adjustment to make the p-value not significant anymore. And if we just use the traditional logistic regression, so that means from this study we cannot get the significant result. And similarly to this the BMI 85 plus, so we still find so for the traditional logistic regression, it dilutes the result to make it not significant anymore. And so coherence balancing can give us the better result actually. So here I put a summary for all this method I introduced today to give conclusions. Is it a parametric models? Is it a functional assumptions? It has a probabilistic interpretation or not? And we can make a simple comparison for all of these method models in when you do the probabilistic score adjustment method in practice. You can think about which method is more appropriate for the data for your model you can use. The conclusion, so we need to choose the models with appropriate interpretation for the specific adjustment with emphasis in this talk, and select the sufficient and effective covariates. So since our fundamental assumption is an ignorability assumption, which means no hidden bias, so we hope this probabilistic score can catch as more as confounding information as possible. And also check the model assumptions and their given data before we use it. And diagnosis for model validity for both the accuracy and the generalization. And definitely some future work we need to do more. As a statistician, we need to do more simulation study to compare the model performance and the different. So we have a multiple choice, but each method may provide for different type of data structure. So we so far there's no unique rule to tell you which data is more which method is the best choice for some specific data. So we may need to do more work to help them to make their choice there. So also statistical inference under high dimensional data. This is a very emerging questions. Actually, the high scale data become more and more, and it's become very difficult to do a good estimation, no matter for the probabilistic score model or for the outcomes model. So we needed to do more work to get a better estimation of model inference for this large scale high dimensional data.
Any questions?
So I think you alluded to it at the end, but when do you choose what?
Okay, simply speaking, we know usually we use the propensity score matching and the propensity weighting method, right? In practice. So if you would like to use the propensity score matching, the key point is you need to guarantee you have the optimal current balance, right? So we would like to, based on one estimated score, we would like to have the optimal balance between two groups. However, traditional logistic regression does not guarantee that. Since the estimation based on logistic regression is to maximize the likelihood, not to balance the current distribution. So that means I can show you some formula. So this is called the coherent space-based model. So the coherent balance based propensity score. So here we specify some of the probability. This P means the probability function for the propensity score, and this Z is also the indicator variable of treatment assignment. So instead of the traditional logistic regression to maximum the likelihood function by solving this score function equals 0, the author proposed to rewrite this term as a distribution, the first and second moment of the covariance. As long as this condition is true, so we can basically make sure, based on this observed data, we can optimize the first and the second moment distribution of this observed covariance. So actually, first and second moments of the distribution catch the most information of a variable. So we know the mean. The first moment means the mean value, indicate the mean of a distribution, and the second moment means the variation of a variable. So usually, based on the first and second, we can catch most distribution of the particular variable. So that means traditional logistic regression cannot guarantee that. But if you would like to use the propensity score weighting method, we more prefer the interpretation of the probability of treatment assignment. Since we in propensity score matching, we use the sampling weight. We use the score as a sampling weight to generate a whole population. So this weight is defined as a probability of sampling. So we use a rebate, or no matter you use the inverse probability weighting or some other technique. So so depend on your purpose. So the trends depend on your purpose. So what kind of model you would like to use to do the
So, for example, for Deberancel's study, why did you use the method that you use? I think you use the covariance balancing.
Yeah, I use the covariance balancing. So first of all, we still use a weighting method. So we care about the probabilistic interpretation. So if we use some machine learning based method, so most of them is not based on the probabilistic framework. So the propensity score value is just a score to use to classify or to balance the covariance treatment assignment. It's not being used to interpret as a sampling weight. So that's why. So for that study, I prefer use the logistic regression type of model or even parametric type of model. Another issue is also, since in her study, a lot of covariance is not continuous. It's just a categorical or binary variable. In that kind of data, so the logistic link function may not be satisfied very well. So we know we would like to find some this has to have curve to to make sure our assumptions for logistic regression being satisfied. However, if this is continuous, it's easy to generate that. But for categorical, it's not that close to that kind of type. Since we only have the two type. The dot is just from here and here. It's not any distribution. So I didn't say the logistic regression is not good for. It's not okay for that model, but we want to provide a more robust estimation based on the data. Or actually, we just have initially we have even about 20 covariates. So we know even for some particular variable, the logistical assumption being held, but it may not guarantee it can be held for all the covariates, especially when the covariance number is large. So definitely, people more and more prefer the robust method.
Thank you.